Hello DSAC 2000. In this video, I will be introducing you to the first part of Unit 3 on tidy data. Please pause and read this objective slide. This part of Unit 3 is meant to give you a framework so that you know how to structure data so that you can do things like analyze it and execute machine learning algorithms on it. This first part of Unit 3 is on tidy data. This is perhaps one of the most important things that you will do as a data professional. I would say about 80 to 90% of my time as a data professional is restructuring data so that I can work with it. I cannot overstate the importance of knowing how to tidy data before you analyze it. You will notice that very few textbooks address this topic of tidy data. The reason why it isn't addressed very much in textbooks is because it is very difficult to describe how to tidy data in a textbook. It is something, in my opinion, that is best learned through practice and experience. The steps that one takes to tidy data is not the same for every situation. It is important for you to get acquainted with the material in this section of Unit 3. I've observed that hiring managers are finding that students coming out of data science programs are having an expectation that companies will already have data that is cleaned out so that you can perform machine learning and statistical modeling on it. This is not the reality in the vast majority of companies and has never been the case in every company I've worked in. So knowing how to tidy data is an essential skill for you to be acquainted with now so that you're comfortable with it by the time you enter a job. What is tidy data? Tidy data is data that satisfies all of the three following rules. Every variable has to have its own column, every observation has to have its own row, and each value has to have its own cell. To see a graphical example of what I mean, you can look at figure 12.1 of R for Data Science, which is one of the textbooks mentioned in the syllabus. This is figure 12.1 from the textbook R for Data Science. Observe how this textbook describes tidy data in this one figure. Every variable or attribute has its own column. Country has its own column, year has its own column, cases has its own column, and population has its own column. Every observation has its own row. In this situation, every observation is uniquely identified by the country and the year. Thus, every combination of country and year has its own row. Hence, every observation has its own row. In addition to this, every value has its own cell. This cell right here has only the country corresponding to the first observation. This cell right here has the year corresponding to the first observation. I do not want to put these two values inside one cell. So that is what tidy data is, and you will see more examples of this as you go through the class. The first thing I want to start off with is that data that are tidy are not necessarily ready for display in a report. What might look aesthetically pleasing might not be tidy. You have to keep in mind that when you're structuring data so that it is tidy, it is mainly to optimize usage for a database or for use for analyzing with a programming language. Tidy data is not necessarily data that is appropriate for a layperson audience to be looking at. Tidy data, however, is optimized to allow for storage in a SQL table and to allow for fast analysis. So this is just explaining that when I refer to a tidy data set, I will just call it tidy data. Why should you care about tidy data? I've mentioned already that the tidy standard is a standard for storing and shaping data. It is necessary to have a standard when you have a lot of data to work with. You need a framework to start off with so that you can structure your data and optimize your work. It becomes even more of a necessity if you're in a company that uses a lot of spreadsheets. The thing with programs like Excel is that they're both a blessing and a curse. They give the user a lot of flexibility about how to structure data, but when you need to do really fast data analysis, if you don't structure your spreadsheet properly, it may slow down things that you need to do with the data. In addition to the tidy standard being a standard for storing and shaping data, data that are tidy allow you to create variables from currently existing variables. Variables that are created from currently existing variables are known as calculated fields, and you'll get a taste of what this means later in this class. Here is a good example of tidy data. This is Fisher's iris dataset. I'm going to show you how to view this dataset in R. Start off by opening your DSci 2000 folder with your GitLab repository. Remember, the first thing that you're supposed to do whenever you want to use RStudio is to start off by opening up your R project file. So now we have RStudio open. I'm going to start off by going to File, New File, and then R Script to create a new file with R code. What's really nice about R is that it has pre-built datasets. The iris dataset is one of these datasets. I'm going to type in iris, and with my cursor to the right of iris, I'm going to execute that one line of code. How you do that is you press Control Enter. And now I'm going to zoom out and look at the bottom left at the console. This is Sir Ronald Fisher's iris dataset. For those of you who are not familiar with Fisher's iris dataset, each row represents a flower that was measured. For each flower in each row, Fisher gathered the species of the flower as well as 4 different measurements of the flower. This is tidy because every observation is a flower. In this situation, each row represents a single flower. Thus, every observation, which is a flower, has its own row. In addition to this, each observation's attribute, such as sepal length, sepal width, petal width, and species, has its own column. So we have that every single row represents an observation, which is a single flower, and every single column represents an attribute of an observation. In addition to this, only one value is inside each cell. Because this dataset meets all 3 of those conditions, it follows that the iris dataset is tidy. Because the iris dataset is built inside of R, you can scroll down the console, click to start the cursor, and type in $iris to learn more about the iris datasets in the help screen. Please feel free to read through this documentation so that you understand what is in the iris dataset. So because in the iris dataset, each row represents one particular flower, and each column represents an attribute of the flower in the given row, and each cell represents one particular value, it follows that the iris dataset is tidy. Let's consider another example. What I'm going to do is I'm going to open up my DSci 2000 folder, and I'm going to start a new folder called Unit 3. I'm going to again open up the R project file, and then using this bottom right window, I'm going to navigate to the Unit 2 folder. I'm going to open up the code.r file. Recall that this was the code that we used to connect to the SQL database. Please copy this code, new file, and then R script. I'm going to paste the code in here. Observe that this code's file name is in red. We're going to save this code to the Unit 3 folder. So I'm going to go to File, Save As. I'm going to save it into Unit 3, and I'm just going to call it code.r again. So now that you saved code.r in the Unit 3 folder, I'm going to make one change to this file. We are going to change SQL Query to SQL Fetch with a capital F, and we're going to collapse a string into one line and type in real underscore estate dot realtor underscore metrics. I'm going to press Control S to save, and the next thing I'm going to do is this. I'm going to run the code just like I demonstrated to you in Unit 2. I'm going to select all using Control A, and then I'm going to press Control Enter. It prompts me for my database username. I'm going to put in my database username, and then next I'm going to put in my password. So now that I've executed my code, I'm going to go to the top right of RStudio, make sure that the Environment tab is clicked, and click on DF. This dataset on the top left is a table of real estate metrics. Observe here that there are 2 different types of values. The median listing price, which is the median listing price of a house in the Twin Cities area, and the days on market, which is the median number of days that a house is in the Twin Cities market before it is sold. Observe here, for example, that this value of $352,500 represents the median listing price in January of 2019. This is the same value right here, except for February of 2019. These two values represent two completely different observations. Thus, these values should be in their own rows if these data were tidy. Thus, because each observation does not have its own row, these data are not tidy. If we go back to code.r for your Unit 3 version, change this string realestate.realtormetrics to add _long to the end of the SQL fetch. Select all with Control A and then press Control Enter to run your code again and put in your credentials. We're going to go to the right again to the Environment tab and click on DF. If we scroll to the left, we see the same data set, except now the data set is tidy. Each observation is determined by the type of statistic we have, which is the median listing price in this case, as well as the month and the year. Every month has its own row. So this is what a tidy version of that prior dataset would look like. Each observation has its own row, and each attribute has its own column. So if we look at the tidy version of this dataset, the following columns uniquely identify an observation. The type of statistic you're looking at, because the statistic is either the median listing price or the days on market, as well as the month of the statistic and the years of the statistic. These three columns, statistic, month, and year, uniquely identify each observation. For that reason, we call the statistic, month, and year altogether a primary key for this table. Primary keys are unique identifiers for every observation. Another phrase that I will use instead of primary key is unique identifier. Unique identifiers are extremely important because they all uniquely identify an observation, and we want our observations to be easily identifiable when we look at a single row. Primary keys are usually contained within a single cell. However, in this situation, the primary key is split among three different cells, namely the statistic, month, and year. When you have a primary key that is split among multiple different cells, you call it a composite primary key. So this table has one composite primary key consisting of the columns statistic, month, and year, which uniquely identify every row of this table. For general advice of how to appropriately design a table, here are two general tips. Every primary key, or every cell that is part of a composite primary key, should constitute a variable and therefore its own column, because we want the data to be tidy. And secondly, by convention, the primary key, or every cell that constitutes a composite primary key, are on the leftmost columns of a table. In this situation, we observe that every value is uniquely identified by the statistic, month, and year. Because those values uniquely identify an observation in this table, they should be on the leftmost columns of the table, so that when you're scrolling through this table, you can look at the left side of the table and know what values uniquely identify each observation. There are two attributes that describe the ideal structure of a SQL table. Tables should be tidy, so they meet the three conditions of one observation per row, one attribute per column, and one value per cell. And tables should contain a primary key, which is ideally on the leftmost columns of a table. And remember, the primary key uniquely identifies an observation. The iris dataset does not have a primary key, but it is tidy. Why is this? If I look back at the iris dataset, I can see that it is tidy because every observation has its own row, and each attribute has its own column, and each value has its own cell. However, there is no primary key for this table. A primary key, recall, is a set of columns that uniquely identifies each observation. This dataset has 5 columns: the sepal length, sepal width, petal width, and species. You could theoretically have 2 flowers that have those same exact attributes. Because it is possible for all 5 of those attributes to be duplicated among different flowers, none of these 5 columns can constitute a primary key for this data set. Because there are no other columns than these 5 columns, there is no primary key in the iris dataset, despite that it is tidy. So in an ideal world, tables should be tidy and contain a primary key. The iris dataset does not have a primary key, but it is tidy. The real estate metrics dataset is tidy because each observation has its own row and each attribute has its own column, and in addition, each row is uniquely identifiable by these 3 columns: the statistic, month, and year, which constitute a composite primary key for this table, because the primary key uniquely identifies every observation. Because the iris dataset does not have a primary key, I personally would strongly discourage putting it in a SQL database. These principles will be more clear as you go throughout the class. The main point I need you to get from this lecture is this: whenever you are designing a database of tables, your tables should be tidy and they should contain a primary key. You should be able to describe what a tidy dataset looks like and what it doesn't look like. And you should also be able to point out what columns constitute a primary key of a table. This will be especially important when we cover joins in the next unit. I want to just mention a very quick side comment on what I call the generalizability and adaptability of data structures. Whenever you are designing a table, you need to make sure that your table is generalizable and adaptable to new data. For example, let's say I'm working with this real estate realtor metrics long table. As I mentioned earlier in this lecture, there are 2 statistics that are currently being collected: median listing price and days on market. What if I decided one day that I was no longer going to collect median listing price? What would happen is that would just stop me collecting additional rows with median listing price. But let's say instead that I had thrown median listing price into its own column. What would happen in that situation is if I suddenly stopped collecting median listing price, is I would have a bunch of values in a median listing price column that would be suddenly blank. And as I keep adding observations, I keep adding blank cells in my table, which is wasted space. For that reason, the principle of tidy data actually adapts to what happens when you want to add new metrics to a dataset or when you want to just stop collecting certain datasets. You'll get a small taste of this in this class, but for practical reasons you need to be aware that tidy data allows you to be generalizable and adaptable to when your data changes. As a general rule, it is always easier to modify rows than it is to modify columns. Because if you, for example, stopped collecting data that was located in a column entirely, you would get a bunch of blank rows. If you wanted to add data that existed in a new column, you would have a bunch of blank rows before you added the column. It is always easier to make sure that your observations are in individual rows, because rows will not demand nearly as much change. To end this video, I'd like to show you one more additional example of a dataset which you can find yourself in R called the empty cars dataset. The empty cars dataset consists of several observations dealing with certain makes and models of cars. Each observation in this dataset is uniquely identified by the make and model representing that row. Thus, the make and model constitute a primary key for this empty cars dataset. These columns represent attributes relating to the cars. So these data are tidy because each observation, which is a make and model, has its own row, each attribute has its own column, and each value has its own cell. In addition, the make and model constitute a primary key for this table. Now that we're finished with the lecture, as you want to get into the habit of doing the class, make sure you save your code.r file in your Unit 3 folder. Make sure that you've pressed Ctrl S, and then right-click on your DSci 2000 folder, go to Git Bash here, CD to your Unit 3 folder, and then git add code.r, and then do a commit on it. And then push this to GitLab. Make sure you get into the habit of doing this after every lecture.